Hi, my name is Gavin, and this is the video for Design Assignment 1 of Computational Multiphysics. On screen you can see my group. In this assignment we were given a scenario of a two-stage rocket that shot straight up into the atmosphere with a 200 kilogram payload. Our goal was to find the optimal amount of mass of fuel to put into both tanks such that upon exiting the atmosphere and exhausting all fuel, our rocket has the maximum amount of kinetic energy possible in the scenario. We must spend $3 million over the cost of fuel, the tank, and engine masses in this assignment, and my contributions consist of brainstorming with the group initially. I wrote a flex program to model the rocket problem. I implemented that program into a preliminary Python program that executed a grid search over every possible mass. I wrote the problem definition for the document, I helped in writing the analysis, and I wrote the explanation for the scripting part of the document. Here's an FBD of the rocket as it travels strictly upward in the RY direction under the influence of drag, gravity, and thrust. We divided this problem into three sections, the first consisting of the mass of both stages in the payload, second of the second stage in the payload, and the third of just the payload. If we go down, we can see all the constants in flex modeled by the red code here, alongside the time relations for each fuel tank to deplete, which are then taken in conjunction with the mass at each stage as I've defined, connected to an overall mass variable that defines the mass of the rocket at a given point in time in the simulation. Here we can see the thrust force equation alongside the gravity force equation, both modeled in flex, alongside the drag force and air density relations, also modeled in flex in red code there. Here we can see the cost function for flex alongside the acceleration of the rocket at a given point in time in flex. Here's the kinetic energy after both stages have been dropped, and here is a maple code relation to define the mass in tank 2, solely dependent on the mass in tank 1, so that we only have one variable to optimize in Python. And here we can see the Hall condition for after it's left the atmosphere and dropped both tanks. To test our model, the first thing we want to test is the trajectory. What we expect is to go straight up in the RY with no x variation. That's exactly what we see on screen with two mass configurations, both on a scale of e to the negative 13. They go up in the RY and they don't move in the x. Coming down to an edge case, as we go higher and higher into the sky, we expect the drag force to go down with air density, gravity to go down as we get farther away from the center of the Earth, and we expect thrust force to stay the same. Due to that balance of forces, we should accelerate faster and faster the higher we get, which you can see exactly right here. And then once we drop down to here, that is after all the fuel's been exhausted, the thrust force stops, and then all we're left with is gravity's almost negligible effect. Now, in a scaling case, we're going to increase the mass of the payload with each iteration of this flex, and we can see it's traveling lower and lower into the sky until it doesn't even pass the troposphere and drops all the way back down to the Earth. To optimize our program, the first thing we did was implement a statement into Flex that allowed its data to be printed onto a text file for Python to later access. After that, we did a grid search over every possible mass in fuel tank 1 based on the previously defined relation, and we can see that in this graph right here. The max value must be somewhere within the range of 30,000, so we did a zoomed-in search over that value, and we can see that we will make our higher bound 34,000 and search within a range. So taking a look at the final code here, we can see that preliminary grid search done to generate the previous graph is implemented into this for loop, which is nested in this while loop. This way we can modify the grid search range after the for loop finishes its search to the current range generated by this statement right here to make it smaller and smaller and run the grid search over and over again, each time with a smaller range. Now each time this nested for loop runs, it takes the maximum energy index and assigns the bounds of the next range to be the left and right indices of the current list of mass values. That's done in these statements right here. The while loop keeps performing these grid searches over smaller and smaller ranges until it's within a small enough step size as defined in the code here, if the step size is less than 250 kilograms, such to make found true and break the while loop so the code will continue below. Then after that, a curve is fitted to the output graph, as can be seen right here through these lines of code, such to average over the noise present in the values. Even though they are interpolated for higher accuracy, there will still be a large degree of noise. Therefore, that's the reason we decided to do this curve fitting implementation. Now, the max value is then taken from the curve, and that is what we take to be the optimal mass for tank 1. The graph can be seen right here alongside the progress report that is printed as the simulation runs. Therefore, upon running our optimized program, we found the optimal mass for fuel in both tanks to generate the maximum kinetic energy upon leaving the atmosphere and exhausting all our fuel to be, for tank 1, 30,991.647 kilograms, and for tank 2 to be 5,126 kilograms, both with an error of 132 kilograms, which is coming from the step size used in the final simulation. Due to this fuel configuration, the maximum kinetic energy is then 12,270,362,706.7 joules.